Hi there, let's look at LeetCode number 22 called generate parentheses. The problem statement, given n pair of parentheses, write a function to generate all combinations of a well-formed parenthesis. Before looking into the examples, let's look at the framework we'll use to solve this question, the race framework. If you already know from our previous videos what race framework is, you can skip ahead to the next chapter, else please follow along. Let's look at the RACE framework for data structures and algorithm questions. We have designed this framework to help you put some structure around lead code type questions. We recommend you to use this framework while answering your questions in interviews, and also use this framework when you're practicing lead code questions on your own. Let's look into how this framework works. So RACE is an abbreviation where R stands for reason, A for approach, C for code, and E for evaluate. When you're presented with a DSA question, the first thing that you do is you start reasoning about the question. This is a section where you reread the problem statement, you ask clarifying questions if it's an interview setup, and you look at the examples. Your end goal from this section will be to get a very solid understanding of what the problem statement is saying. With that understanding, we move on to the approach section. Here, we think about different ways the problem can be solved, evaluating different approaches. The end goal here would be to focus and finalize on one approach. If you're in an interview setup, you talk to your interviewer about different approaches, and with the consensus approach is finalized, where you focus and dry run that approach to make sure that your approach works on your question. With your approach being finalized, next we move on to the code section. This is where you translate your approach into a working piece of code. This is also the section where you dry run the code on a few examples that we saw in the reasoning section and hopefully also worked with in the approach section. You run your code and make sure that all your test cases pass. Finally, with code complete, we move on to the evaluate section where we write big O notations for our time and space complexities. Please don't worry about memorizing this framework. We'll use this framework for all the DSA questions that we post on Soulbits channel. Let's start looking into the first section, which is the reason section. So here we'll look at the question, we'll reread the problem statement and make sure that we understand what the problem asks us to solve. So here, problem statement says that we are given n pairs of parentheses and we have to generate all combinations of well-formed parentheses. So if we look at an example, let's look at example number 2 here, where n is given as 1 and the valid parenthesis is open and close. So please note here that this cannot be a valid parenthesis. It has to be a valid parenthesis in the sense that whenever you open a parenthesis, it always gets closed and the parenthesis is always opened first. It's not like you can close the parenthesis first and then open it. Let's look at another example for n equals to 2. One of the combinations that you can have is either open, open, close, close, or you can have open, close, open, close. Now if we start making a few observations, we'll see that number of open brackets in a well-formed parenthesis is equal to number of closed, which is equal to n, the n which is given to you. So in this case, a number of opens is equal to number of closed, which is 2. Another observation you can make is at any point when you are creating a well-formed parenthesis, for example, the first case here, when we created this parenthesis, number of open braces is always greater than or equal to number of closed braces. So if a parenthesis has to be well formed, this has to satisfy at all times. Another observation that you can make here is number of open braces will always be less than or equal to your given n, and so will hold true for C. So both O and C, which is number of open braces and number of closed braces, they are always less than or equal to n at all times. So intuitively, whenever you are building a well-formed parenthesis given n, for example this one, you always decide to whether add an open brace or a closed brace. For example, for this use case, when you start, since you cannot add a closed brace, the only choice you have is you'll add an open brace. And the next choice that you will make is again to either add an open brace or a cold brace. So it can either be a closed brace or it can be another open brace. So this is where you have, this is what at all times means. So at all times when you are incrementally building your answer, your following constraints, these 3 constraints, they should satisfy. Let's start building on that and further create a decision tree. So let's talk about a decision tree where we start with the following parameters. an empty parameter, number of open braces, which is 0, number of closed braces, which is also 0. Okay. And from this root, we decide on two choices, which is either we add an open brace. So either we add an open brace, and in that case, number of open braces will become 1, closed remains 0, or we add a closed brace. Here open will remain 0, but closed will become 1. Why I wrote this in red is because this is an invalid use case, because we have a closed brace where C is 1 and you violate one of our conditions where C is no longer less than or equal to number of open braces. This means this hits our terminal condition and we will not go any further than this in this branch. So next, we keep working on our left of the tree. So here we take the same decision. Either we add a open brace, so we add another open brace where O will become 2 and C will remain 0. Again, it's still a valid case. Or we add a closed brace. So O will be 1 and C is 1. All good. We are still satisfying all our constraints. Let's keep working on that. So here again, we have a choice of either add a open brace. Now O here will become 3 and C will become 0. Or we add a closed brace. So open will remain 2 and C will become 1. Here again, our n, we are working for n2. So this becomes an invalid use case because our O is 3 now. And we know from our constraints, O always has to be less than or equal to n. So here n was 2, O is no longer, O is 3, which is no longer less than or equal to 2. So this is again a use case where we hit our terminal condition and we go back. We can keep working here. Eventually, if you start building out this tree, this will give you an answer where you'll get this as your valid parenthesis, and O will be 2 and C will be 2. And here, if you keep working on this tree, you'll get an answer here where O is again 2 and C is again 2, and your answer would be this open, close, and open, close. I've cleaned up a little bit and recreated this decision tree for n equals to 2. So if we start from the root where O is 0 and number of closed braces 0, and we start with empty string. So on the left, we take the decision of adding an open brace, which is this use case where we added an open brace, incremented our counter for O equals to 1 and C remains 0. Similarly, on the right, we added a closed brace where C becomes 1. But as we know, this becomes our invalid use case because C is greater than O. This is something that we cannot have in a well-formed parenthesis. So this is where we go further. Here again, we take the decision. On the left, we add an open brace, increment O 2, and C becomes 0, which it was. On the right, we add a closing brace. So here we get like an open and a close. So O and 1 are equal. So on the left side again, we start with the same. Here we add an open brace, and when we do, 2 becomes 3 here for number of open braces, which makes this a valid use case again. So this one becomes invalid. So continuing from here, where we had open 2 and close 0, as we can see in our example, we add another open brace here, and with that, open braces will become 3 and C will become, it is still 0. This again is an invalid state because O is greater than n. Continuing on the right here, we add a closing brace, and where we get this intermittent state, which is a valid state. Going down from here to the left, we add another open bracket where O becomes 3, which again invalidates this state for the same reason, because O is greater than n. We keep going, and for the right state here, we add a closing brace now, where we get open, open, close, close, and this becomes our 1 answer. Similarly, if we jump to the right of the tree, because the left tree is done, so now if we come to the right of the tree, here O was 1, C was 1, so on the left we add another open brace, O becomes 2 and C is 1, which is a perfect intermittent state. From here again we go left, where we added another opening brace, making O as 3, which invalidates this state again because O is greater than N. Whereas on the right, we add a closing brace and making closing to 2 and opening to 2, making this as a valid state. Similarly, for this subtree, if we go to the right, we have added C to 2. This is also an interesting case to notice because this becomes an invalid state because C here is greater than O again. So this becomes an invalid state. We got our two answers in the leaves. And while you observe that these are the two answers that we wanted, here another thing to understand or observe here is for both these answers, O is equals to C equals to N. So this condition holds, which is what our first observation was. We looked at this decision tree for n equals to 2 and observed how we get our results. And we also saw how the observations that we did in the starting of our question, how they apply on our valid and invalid cases. Okay, with that, we have sort of finalized on our approach. We intuitively translated making a decision of adding either an open brace and or a closed brace to a decision tree. And this sort of also finalizes our approach. We can use a recursion based approach backed by obviously a decision tree. Let's now move on and look at the code. So this is what the code will look like. We have our generate parenthesis function, which calls our actual recursion function. Our recursion function has three parameters: current, which is equivalent to this first parameter here, and then like this open and close, we have the open parameters to count the number of open braces, close to count the number of closed braces, and n, which is the total number of n that we are given in the question. We give that a call. The first three statements in the recursion function are our terminal statements, which are the observations that we made in the start of our question. The second two calls are either choices to either add an open brace or a cold brace. So if we add an open bracket, we increment open, and if we have a closed bracket, we just increment close. So it's very similar to our decision tree. With that, let's move on to our evaluate section, where we look at the space and time complexity for this problem. The time complexity for this will be based on something called Catalan numbers. And the big O notation for that comes out to be 4 to the power n over. So that's what our time complexity will be. If you don't know what Catalan numbers are, I'm planning to make a video in the future. So please stay tuned in. The space complexity, however, will also depend on the output. So which is O of n plus we'll have Catalan number at play again. If you want to simply say that, I know this is a fairly complicated expression. If you want to fairly say, you can just say that it'll be a exponential complexity. So 4 to the power n is exponential, which can be standardized as e to the power n. So this can also be written as e to the power n, where e is a constant, e is 4. And you can do a similar simplification in space complexity as well. With that, we complete the problem to our generate parenthesis problem. We use the race paradigm to look at this problem and create a very intuitive decision tree followed by code and then evaluating our complexities. Thank you so much for watching and see you in the next one.